Every so often, a single idea comes along that just changes everything. And in the world of AI, that happened in 2017. A single research paper dropped, and honestly, it's the reason we have the kind of AI we're all using today. So let's dive into this thing. Let's really look at how this one paper completely reinvented the game.
All right, so for years, researchers were banging their heads against this one massive problem. How can you get a computer to truly understand a sentence? I mean, not just read the words, but to get it, to understand the connections, the context, all the little nuances that give it meaning. It was a huge, huge challenge.
And the breakthrough, well, it came from just flipping the whole approach on its head. See, the old way was to process a sentence one word at a time, in order, the way we read. The new way, forget that. Just process all the words at the exact same time. And the shift from going in a straight line to seeing everything at once, that was the game changer.
So to really get why this was so revolutionary, we've got to take a step back. We need to look at what came before and why it was just hitting a wall.
Before 2017, the kings of the castle were these things called recurrent neural networks, or RNNs. They were the absolute state-of-the-art for language. And their design kind of made sense, right? They read a sentence word by word just like a person, creating this sort of running memory that got passed from one word to the next.
Okay, imagine you're trying to read a long sentence, but you can only look at it through a tiny little peephole. You see one word, then you slide it over, see the next word, and so on. That's basically what an RNN was doing. It makes sense, but man, is it slow. You can't see the second word until you're done with the first. Everything has to wait its turn.
And the paper itself just nails it. They say this step-by-step process, it's a fundamental constraint. It creates a huge bottleneck. See, you couldn't just throw more computers at the problem to make it faster. The process itself was the slow part. And that meant there was a hard limit on how big and smart these models could ever get. And this is where everything changes. This brings us to the big moment. In 2017, this team from Google publishes a paper with a pretty simple title, but inside was an idea that was a complete break from everything that came before.
I mean, just think about how bold this is. They're basically saying, hey, you know that thing everyone's been doing for years? We're throwing it out. Completely. They propose this new thing, the transformer. And the whole idea is to get rid of recurrence, get rid of convolutions, just toss them. They decided to bet everything on one single concept, attention.
And this is the new superpower. It's called self-attention. So remember that peephole analogy for RNNs? Well, self-attention is like throwing the doors wide open and getting a full panoramic view of the entire sentence at once. It lets every single word look at every other word in the sentence, all at the same time, and figure out how important they are to each other. It doesn't matter if they're right next to each other or at opposite ends of the paragraph. The distance just vanishes. All right, so let's get into the guts of this thing. How does this new transformer architecture actually work? I mean, really, how can you understand a sentence if you're not even reading it in order? Let's take a look.
Okay, here it is, the original diagram from the paper. And yeah, I know, it looks a little intimidating, but let's just break it down. At a high level, it's really just two big pieces. On the left, you've got the encoder. Its job is to read and understand whatever you put in. On the right, you've got the decoder, and its job is to generate the output, like a translation. So, information flows in, the encoder chews on it, passes it to the decoder, and the decoder spits out the answer. And the engine that powers both sides, you guessed it, that powerful self-attention we just talked about.
But the authors didn't just stop there. They thought, why look at a sentence from just one angle? So they came up with something called multi-head attention. Basically, the model runs that whole self-attention process multiple times, all in parallel. In the paper, they used 8 heads. And the cool part is that each head can learn to pay attention to different kinds of relationships in the text. So what you end up with is, it's like having a panel of 8 different experts all looking at the same sentence at the same time. One expert, or head, might be really good at grammar. Another one might focus on who did what to whom. A third might be great at figuring out what it refers to from 3 sentences ago. And when you combine all those different perspectives, the model gets this incredibly rich, deep understanding of the text.
Okay, so this brings up a really obvious question, right? If you're looking at all the words at once, how in the world do you know the difference between the dog chased the cat and the cat chased the dog? The meaning is completely different. Word order is critical, and it seems like this whole parallel idea just throws it out the window. Well, the solution they came up with is just so clever. It's called positional encodings. Before anything else happens, they add a unique little signal to each word. Think of it like a digital timestamp. This little bit of math tells the model, hey, this word is in position 1, this one's in position 2, and so on. So you get the best of both worlds, all the speed of looking at everything at once, but the model still knows the original order of the words. It's just elegant.
Okay, so it's a really cool and clever idea on paper. But the big question is, did it actually work? How did it perform in the real world? Well, the results weren't just good, they were shocking.
I mean, look at this table from the paper. This is a standard translation test, English to German. The score is called a BLEU score. All you need to know is higher is better. The best models from Google and Facebook were hovering around 26, and the Transformer? It blows past them with a 28.4. It didn't just beat the competition, it left them in the dust. And look, it didn't just squeak by. It beat the best models out there, including these huge, complicated systems from Google and Facebook, by over 2 full points. Now, to you and me, that might not sound like much, but in the world of machine translation, a jump that big overnight is just massive. It's a huge leap forward. But here's the kicker. It wasn't just more accurate, it was also way more efficient. The Transformer wasn't just stronger, it was also faster and a whole lot cheaper to train. The paper says it took just a small fraction of the training costs of the other top models. So you had something that was better, faster, and cheaper. That's the whole package.
So what we're talking about here, this wasn't just another small step forward. The Transformer was a totally new path. It didn't just break a few records, it kicked off a full-blown revolution in AI.
So why was it so much better? This table right here really gets to the heart of it. Just look at that last column, maximum path length. With the old RNNs, for the first word to talk to the last word, the message had to pass through every single word in between. The longer the sentence, the longer the path. But with self-attention, the path between any two words is always just one step. The first word can connect directly to the very last word, instantly. This is what gives it this incredible power to understand context, even in super long documents. So when you boil it all down, the Transformer did a few incredible things. First, it unlocked this massive ability to do things in parallel, which let us train way bigger models than ever before. Second, it cracked the code on understanding context over long distances in text. And finally, it became the blueprint, the literal foundation for pretty much every major AI model that came after it. We're talking BERT, we're talking GPT, all the stuff that's changing our world right now. So yeah, the ideas in this one paper, attention is all you need, they fundamentally changed how machines understand our language. It's what kicked off the whole generative AI boom we're living through. And it really leaves you with a huge question, doesn't it? This architecture unlocked language. What's it going to unlock next?